welcome Dr. Michael Bodunrin from Johannesburg, South Africa. He's a senior lecturer in Witwatersrand University in Johannesburg, and he works on a lot of metallic systems, for example, high temperature steels, pre-resistant materials, titanium-based alloys, and so on. And some of his work on aluminum-based metrics are very highly cited, more than 700 citations on one of his papers, so that's commendable. And we met in one of the Bodunrin Research Conference in 2019, and since then we have been in touch and we have been talking about work and otherwise. And so this time again, he was visiting US for a Bodunrin Research Conference, and so I invited him here. So and he graciously accepted to come and talk about his work. Other than research, he has also been engaging with SciBridge and working with them to emphasize on STEM education in East Africa and South Africa. So it's a good opportunity for us to show him the capabilities which are being used to send different resources to East Africa from NC State. So welcome, Michael, and I encourage you to talk about your work. Thank you.
Thank you so much. Thank you, everyone. Thanks for coming, and thanks for having me. Again, I am Michael Bodunrin, but that might be difficult to pronounce, so just call me Michael. I'm from Wits University, and where are we? We're actually, so we're in Africa, and we want you to visit us just the way I've visited you. And especially when it's cold in the US, you can come get nice ones in Africa, okay? It's cold in South Africa now, so I escaped the cold. And for the first time since 2007, it snowed in South Africa. So I missed that, but I didn't regret it. So basically, if you come to Africa, you need to really travel down here. This is where we are. And here, you find Cape Town just at the tip there, and you can see where Atlantic Ocean and Pacific Ocean actually meet. Yeah. And again, you can visit Table Mountain as well if you've never been to one, basically. And but I mean, don't go to Cape Town alone. The first place you probably get down is Johannesburg, and that's where my university is. And it's actually a very nice city, as you can see, night. And of course, that's our university, and that's our Great Hall. That's a symbol of our university. If you've ever heard about Frank Navarro, talked about deformation mechanisms and stuff like that. He was in the School of Physics before. So he was also here, was a faculty member long before. And that's our building. It's sorry, it's a bit old. It's as old as the university itself. We turned 100 last year. Last year. And in my school, it's a marriage of chemical engineering and, of course, metallurgical engineering. So we have about 10 research groups and about 350 postgraduate students. That includes honors, masters, PhD, and of course, some of them are already working and some are full-time students. Okay, so we can keep you busy if you can. So it's not only about holiday. We have a few equipments you can play around with. Okay, this is one of them, which is in my own lab. I inherited it. Basically, it's called Global 3500 thermomechanical simulator. I think it was invented after the Second World War here in the US, basically to study weld joints and all that. But now, we use it to study how metals are formed into different shapes and all that. So that's basically my area of expertise. That was me when I was still a PhD student, basically. So I've gained some weight. Okay, and we have XPS machines, back plasma sintering machine as well. For powder consolidation, you can synthesize metallic materials, ceramics, and of course metal matrix composites, basically, and that. And I'm also in charge of this one. So we have like the XRD, different ones, basically the bigs and the big ones and the small ones, but of course we have that one. Numerous potential starts, we are into electrochemistry, and I'll talk a bit about that, corrosion, basically. Then we also have EPMA, and we have a very old SAM. The TEM, I don't use it, it could only analyze powders and all that. And that's one of the reasons why I'm here, because I believe probably of such capabilities that you could have. We have a SEM and we have others in other schools, but in our particular school, we don't use department, we use school basically. So we have SEM as well. And that's our hydrometallurgy lab. So we have a lot of resources. So we process, pure metals from, their ore basically. So we're strong in mining and, metal extraction processing, pyro, hydro, and all that. So that's our hydro. It's usually very dirty. This was when we were upgrading it. So it's not supposed to be this neat. Yeah, that's just out of it. Then we've recently upgraded our welding lab, and our welding technician is a lady. So, and we have a welding simulator that it's a virtual welder you can use to practice. So if you come, it will be a lot of fun. So it's not just visiting different mountains and all. You can do that. So we're probably one of the most equipped universities in Africa. Yeah. So, and we've just got that as well. It's a newly installed vacuum melting furnace, so we can cast up to 10 kg, ingots from there. So that's it. So I get inspiration from many people, but he is one of them because I was about to submit my PhD when he passed away, and as at that time I was winning the first grant. So, and I looked out for one of his last words before he died, and that was it. And I'm going to just read the area in the one on the right one. It says, "We are all time travelers journeying together in the future, but let us work together to make that future a place we want to visit." So the reason why I'm here is that I'm happy to work with you, and I hope that you'll be happy to work with us. And you can see Steve Hawkins really contributed significantly to the way we think about black holes and all that. So, and he thinks that no single man can do it alone. Albert Einstein predicted gravitational force of field. I can't remember specifically now, but it took about 1,000 authors to actually measure that a few years ago. Basically. So it's good to work together. But the one thing that really got me bothered about this statement is he said, make that future a place you want to visit. So how do you visit the future? So, and that really got me worried. And in a way, I came up with an answer. And that answer drives the kind of research that I do. So, because basically, it may not really have immediate impact now, but I hope that if I find answers together with you, maybe it would have impact in the future. So basically, the question that keeps coming to my mind is how do we visit the future? So I thought maybe if we want to visit the future is to be able to pay attention to the problems of the future and try to address them long before they arrive. They've been warning about climate change and all that long before now, but now we're taking it serious. But the damage has been done, okay? And there's still a lot of people. So this really inspires my research, and I'm going to tell you now about my journey into developing low-cost titanium alloys. The question is, are they truly low-cost? We'll find out. The whole idea is, if you look at the population there, geriatric population is increasing at an alarming rate, and by 2050, developing countries, middle and low income earners, we have huge proportion of older adults living in the world. And we know that as you age, the chances of you breaking your hips or your bone is actually going to increase. So in developing countries, how are we going to manage this? Because yes, the treatment is there, but we know that it is quite expensive, especially in the US. But US is a developed country. But we still have the question, how many people can afford if you go through this problem of bone fracture and all that. So you can see I was chatting to, because it's really difficult to come by the exact price of getting titanium implant, for example. So I was chatting to an orthopedic surgeon, and he gave me that rate. It costs between $1,500 and $10,000 to get like hip replacement. And you can see the fraction of what implant costs based on the conversation that I had. I think Belgium seems to have cheaper, cost when you have to replace your bone or anything compared to the US. US is actually the most expensive. So I thought, okay, in middle and low income countries, they probably wouldn't be able to afford that. And what can we do about that? So I thought, okay, maybe if we could make titanium cheaper, but it's not that easy to do. So the general story is really cheap at the moment, and I started considering. And I could give you a little bit of more motivation as to why. So, but I didn't do it alone. As you can see, I'm a helicarrier researcher, so I don't have big funds to get a lot of graduate students and all that. So these are just 4th-year students, like undergraduate students in the final year, who did some part of the work that I'll show to you with me. Basically, and of course, I got a little bit of funds from all these people, organizations that I've actually acknowledged. So, I don't know how much we all know about titanium, but it was discovered in 1791. It took about over 100 years before it was actually processed by Crow. And then we can get pure titanium after 145 years or thereabout. And then if we understand the metallurgy, we can make different alloys. Of all these alloys, this is the most utilized, both in aerospace and for land-based applications. Basically, it's got TI6. Lots of arguments about the toxicity of these alloys in the human body already because of the amount of vanadium it contains, basically. People also make argument about the high amount of aluminium, but there's really no direct evidence of that because aluminium, they've argued that it affects, it leads to Alzheimer's disease, but how does aluminium even cross the blood-brain barrier? We don't know evidence of such. So, but vanadium is something that has been well established. So we all know titanium has excellent biocompatibility, corrosion resistance, and of course it's lightweight. And that's why it thrives in the biomedical environment. And of course, in the aerospace, if you have been in a plane before, definitely you've benefited from titanium. So, but there are other applications you could use it for, but you wouldn't waste a lot of money on that, except for biomedical application, which is still a problem. So, the challenge is that it is quite expensive, and if you compare it to aluminum and steel, that's what the literature says. But this is actually a very old literature because Froese happened to be one of the leading research experts on low-cost titanium alloys, and is an American researcher, basically. I think the figures must have changed recently. Why is it so difficult, or why is this alloy very expensive? For example, it's very difficult to extract it from its ore, basically. The fact that you have it in abundance does not mean you can easily extract it. It took 140 something years to even extract it. That's the first thing. The second thing is it's difficult to process. It's not like steel. I mean, you can even play around parameters and all that with steel, and you still probably arrive at the same. But with titanium, it's very sensitive to slight changing processing parameters, and it's very difficult to machine, and you can see the breakdown here. So, then what got me into low cost CCRE? So, about 2013, South Africa was quite happy because they are the second largest producer of titanium ore in the world. There's a class ilmenite and rutile. So the point that even about 2019, Rio Tinto still invested in extraction of titanium from titanium reserves in South Africa. But the problem is trying to get this ore to a refined state that it can be used commercially in South Africa. So yeah, around 2013, they came up with a method that they patented, and it was all secret, that they found a way to actually extract pure titanium from the naturally occurring reserves. And the whole goal is to have a metal titanium processing industry by 2020. But unfortunately, that was not realized. And again, the second goal they were trying to achieve is to make titanium powder, the pure powder, a continuous process. Most of the method is still based on batch process. So they couldn't achieve the continuous process. Before they did their patent at a very small scale, it was fine, it's very cast fiber, but immediately scaled up, they ran into problem. And this happened around the time when I was about to start a PhD. So we were trying to work with CSR around that time, and we got, there's this noise about low-cost titanium alloys and titanium, low-cost titanium powder, pure titanium CSR out there. But when they tried to scale up, when they built this pilot plant, they had a lot of impurities, contamination. And again, they couldn't produce consistently the morphology they wanted for the powder. I got a bit delayed in my work around that time because we wanted to use that powder for alloy development. But we only got a few, and we characterized, and we saw that it has high amount of iron in it, and that was one of the problems, and other impurities basically. So can we really add value to this iron containing titanium powder? So that was what actually drove me into developing low-cost titanium alloys. So basically, we want to improve. We want to see if we could use the iron containing titanium alloys. A lot of people have said if you add iron to titanium, it's a bad idea. But of course, the results that we have shown, that I will be showing, some of the results I will be showing to you today, seem to prove otherwise. So, so what we did was to just produce a few number of alloys, reducing amount of aluminium, and of course, retaining vanadium and varying the amount of the content of iron and all that. Everything is just to mimic TSS4, which is the standard material that you have in that particular space. And we wanted to see what effect this would have on the properties of these alloys. So, and South Africa invested a lot in the search for new alloys because of the success story they have with 3C out of steel. Basically, it's a ferritic stainless steel, which is cheap, and they use it. They use it in place of austenitic steels in their mineral processing plants, like the Anglo Platinum and all that. So we are also trying to see if we could get unique alloys from this experiment. So to take you through some of the things that we did, so we got the powders with the different compositions that we compacted, produced proteins and 10 grams, 50 grams, and then we got as basic results. So what did we find? So even though we have iron in our alloys, basically we have essential alpha and beta phases in the microstructure. So ideally, when you had iron, if you check the titanium iron phase diagram, when you had iron to titanium, what you would find is that you would have the TIFE phase and of course the HCP titanium phase. So that's what you would have according to the phase diagram. So that's one, and you want to avoid the TIFE intermetallic phase, but we couldn't find that. Probably you have to anneal for a very long time for you to have that one. So that's why we were able to find this, and that was really good for our results. And again, we looked at the hardness of this alloy, and we see that it compares really well with that of, this is commercial grade TICs for our and this is just in the cast mode. We haven't done any more processing on that point. And what is really interesting, and I hope that Prof. Rajiv can give some feedback or we can work on this, is that in terms of corrosion, if you look at all these iron-containing alloys, they have like, the passive region is actually more on the left compared to the alloy that either contain 4Fe or just vanadium. So the TiS4, as you can see here, has actually the passivation current is way higher than all the ones that contains both vanadium and iron. So maybe if you have a cocktail of vanadium and iron as beta stabilizer, you might have some benefit in terms of corrosion performance. And this also reflects in the corrosion rate. I'm just giving you an example of this. You can see how the corrosion rate is much more lower. In this case, where you have either iron and vanadium, maybe it's not a good idea to have just iron as a beta stabilizing alloy to titanium, but have a mixture of both. So we found that, and this wasn't done in actually 3.5 molar H2S. It's actually a very, very corrosive environment. But I told my students later on who worked on this alloys, put it in a enhanced solution, which is similar to how about if you and let's see what you get. And if you look again, with TSS4 there's really no difference. I mean, quite close in terms of performance. Well, yes, we'll see some of this transient current forming in the passive region. But if you look at the corrosion rate that we get, for all the iron containing alloys here, like 10 times in terms of corrosion rate, slower than TSS4. And these contain iron. So and we try to look it up. Why is iron having effect in slowing corrosion rate down? Unfortunately, till today, I haven't seen anyone answer that question. I've seen quite a few people, speculate a lot of things, but there is no concrete evidence, and that's one of the reasons why I thought, okay, maybe Prof. Najee would have some insight on how Prof. Martin could have an insight on how we could go about it. So this is in HBSS, and we saw similar trend in 3.5 H2SO4. So what did we learn so far in that area is that maybe it's not a bad idea to have iron as an alignment with titanium. In fact, the mixture of vanadium and iron seems to be better in terms of corrosion resistance, and that's very, very key if you're going to use them as implant material. So these alloys, we're not proposing them for aerospace applications, basically for land-based applications, because we noticed when we were carrying out a deformation test that it does have low high temperature stress compared to TI6. So basically, for land-based applications, seem to be better than TI6. Basically, so we thought, okay, just having 50 grams is not enough. At least when they patented the powder, when they were trying to make the powder, it was good at lab scale. They created a pilot plant and just slowly changed. So we tried to increase to scale it up. We didn't have the right facility to do that. This particular furnace is used for producing single crystal nickel single crystals, basically at CSIR. So we had to adapt it in a way to produce, a larger scale. And you can see the shaving seems to be quite encouraging. If it's very brittle, you get like very fine chips and all that. That shaving was quite encouraging. And you can see we could carry out tensile tests and all that. And if you look at the microstructure again, it's typical like alpha beta titanium that you would have. Of course, we have some inclusions because that furnace was using the U-track crucible and you see those particles there, basically. And again, you can see the shavings here. The microstructure is starkly standard, what you can see online. So, and again, we checked for the hardness and all that. And we see that it's still fall within the similar range as TI6 basically. So even though it has higher iron content, which is even a better alloying element in terms of cost, because it's about 100 times cheaper than vanadium. In terms of hardness, the properties are the same. And one would argue maybe there was oxygen contamination, and that was why probably the hardness should have went up, or probably that influenced the iron. Hardness in some way, but if you look at the standard TSS4, this is at the limit for oxygen and nitrogen, and you can see that all this were in spec basically. So we just didn't stop at that. We tried to look at the tensile properties. So this time around, we produce all the alloys using that facility that I showed you, and of course, it's not the standard way of producing titanium. But of course, they were all produced under the same conditions, so it's easy to compare all of them. And you can see in terms of elongation, TSS4 seems to suffer. And again, we sent some of these samples to John Hopkins. We got some results. And sometimes that's where collaborations, the record didn't get result on time. But we were able to confirm from their experiment and what we did at box scale. This was a nano-indentation result. We wanted to establish the elastic modulus. And you can see that it's actually similar to what you will have there for TI64, and of course for the alloy containing mixture of vanadium and iron. So this is where we are. We carried out all the tests that I've shown you, but this is where we'd like to go, because we said these alloys can be used for aerospace, but you can use them in human body and stuff like that. And for you to do this, these alloys have to be subjected to some forming processes like hot rolling, forging, and all that. So how do we get here? So we need to check if these alloys can easily be processed. So, and if you read titanium textbook quite well, if you have a lamellar structure, if you really want to improve the ductility and of course in terms of deformation, the deformation properties in general, you desire this kind of microstructure, which is an aqueous microstructure. And if you follow the standard textbook, the most popular textbook on titanium by Bodunrin and Williams, you see that you can arrive at this microstructure using following either of these two routes. And this is usually what you have in the as-cast state, basically. So I thought, okay, I don't want to follow this particular process. Can I vary enough parameter under hot deformation conditions and arrive to at least something similar to this? And I'll show you. So, like I said, this is in my lab, we have this. And I varied in different strain rate and different temperature. I didn't even do any beta homogenization at the beta phase at all. There was just deforming in the alpha beta direction because I believe that that would save some of the cost of the analysis. And this was the initial microstructure basically. So it's a classic Wittmann-Scattini structure, but of course, this was taken the same. But you can't see anything aqueous there or global. So after carrying out those experiments, you could actually, from your stress strain data, you can apply constitutive loading equation, which follows Arena's equation, and you can apply dynamics materials model equation, and that can give you some predictions. Okay, and of course, let me not go too much into this theory. So if you apply constitutive equation, usually when your hand is about 5, you think like you have more dynamic recovery, so you wouldn't be expecting any globularization or any form of aqueous microstructure. But because our hand was less than 5, we have some hope that we'll probably see that. But dynamic materials modeling could help you come up with a map like this, different strain rates and temperature, and you can see regions where you shouldn't even deform the alloys. And that particular region, if you deform the alloy, you would have, this kind of defect. And if you take it to stem, you can see that. So it was really a bad idea to deform under that condition. But what I really want to show is that without following all the 4 steps that have been proposed for processing alpha beta titanium alloys from as-cast to rod state, you can see that we are beginning to form some globules here at high temperature and, of course, at very slow strain rate. Okay, so the question is, we then need to compare. If you do the 4 processes or you do this, which one is cheaper? Okay, but the truth about it is, this is a shortcut to getting the globularized microstructure and not the full microstructure. So that region would be the optimum processing condition for the alloys in general. But now I am focusing on this particular alloys anyway. So what did we learn from there? What we learned is that you can actually carry out deformation and transform the fully lamellar structure into aqueous microstructure by not following that condition. And not all of the lamellar transform basically, but of course, maybe with following it up with recrystallization and annealing, we can get the result that we really want, basically. But generally, if you look at all this process that I've shown you, we can't even achieve more than maybe 20% cost reduction. And if you are making implants that cost between $1,500 and $10,000, 20% is not a lot. So what it would amount to is about $700 to $8,000 per implant from the low-cost alloys that have been developed. So the question is, would middle-income countries be able to achieve it? I don't think so. So we still have a lot of work to do there. But one thing that I bring to here today is to see if it's possible for us to answer that critical question. What is iron doing to titanium that is helping it to reduce the corrosion rate? because most of the argument is iron, has poor corrosion resistance. So why is it that when we add it to titanium, it does reduce the corrosion rate? We know that titanium corrosion resistance is from the surface that forms titanium oxide, that passive film that is formed. Right? And this film now, as you introduce different alloying elements, it changes. But we don't have the capacity to characterize that to see what's really doing. So, and I think that that's something that I would like to, maybe collaborate. And with experts of something also the surface science, maybe could really help. So, but because I thought, okay, maybe titanium will not be cheap enough for, implants, and that's what led me to this other crazy idea. In 2021, that was when I started thinking about it. I only managed to get students to work on it sometimes last year, and then we did like a preliminary experiment, then I got some funding this year to push it a bit further. So normally if you're not using TI64, you would be using 316L stainless steel as the implant material. But the problem with that is very, very dense. So your chances of even experiencing stress shielding effect if you have 316L in your body is actually very high, and that's really not good, basically. But if you go to East Africa, for example, and other developing countries, they still use a lot of 316L stainless steel implants. Of course, in South Africa, the standard now is TI6 because the medical aid system works quite well. So, but the whole idea is by 2050, we need a material that is really cheap. So I thought, okay, can we find another material that's cheap, which is still is generally cheap, right? That can replace 316L stainless steel. And that's when I saw in literature that some people have been trying to reduce the density of steel for some time. And I can go through that quickly. It was first reported in 1933. And then basically they were trying to look for replacement for high chromium, high nickel containing steels, basically these are stainless steels. Then this research died for some reasons that I don't know. I mean, 1958, my father was just 3 years old. So in 2000, then we already came to the reality of climate change and all that. Everybody wants to reduce weight in automobile and all that. Then they went back to it because other materials do not have crashworthiness as compared to steel. So they were trying to reduce the weight of steel, so the density of steel basically. So what they do is you had a lot of aluminum manganese content, and that can give you some reduction in the density. But the problem is in terms of modulus, as you had aluminum, you are compromising the elastic modulus, and that is not good for automobile industry. And that's why you've probably not seen any automobile industry still using low density steel for any application. Especially in Germany and Europe in general, that was the direction. Basically, then it also have pure corrosion resistance because you get different kinds of carbons and all that, and that you can tell have some negative effect of corrosion. But for some reason, this group, they are with their Krabi, basically they published this in 2020. If you could have between 3 and 5% chromium, you can actually improve the corrosion resistance significantly. Okay, and they even argue that it's performed better than 316 stainless steel. And that was what really got me interested in actually confirming what the fact is. Again, another thing that I didn't tell you about this grade of steel is that even in Japan, they're trying to consider it for storage of liquefied natural gas. But it doesn't have any application yet. And I tried to look at materials like that to see if we could find an application for it. And that's why I thought, if it has this amount of good corrosion resistance, according to what these authors claim, maybe we could repurpose it for biomedical alloy. But why am I also very interested? South Africa is the world's largest producer of manganese in the world. I mean, I was having a chat with Prof. Augustine, and she also alluded to this. Basically, and Gabon is the second, basically. So, like all the manganese you use for your batteries and all that actually come from Africa. So, the resource wouldn't be a problem if we can actually find a steel that could be used to produce cheaper implants, basically. So, yeah, so that's more or less the motivation. And so what we did was we looked at literature and looked at typical composition range for alloys, and we normally start our work by doing some thermocard simulations to predict phases and all that, but I didn't put all this in this result. I think the talk is already too long. And then we produce and we do compositional analysis, microscopy, XRD, and of course, then we do like linear polarization, because first thing you want to establish in preliminary studies is what's the corrosion behavior like. And then I love to include my area, like deformation, to see what's going to happen. And I'll show you why this was necessary mentioned. And again, I also have more questions than answer eventually. So this is just one of the preliminary experiments. You can see this is commercial grade 316 system. In terms of the corrosion potential, thermodynamically, it's not likely to corrode. Okay, but in terms of kinetics, when it starts corroding, the low density stainless steel is even 10 times slow. Okay, and this is in 0.9% NaCl and gas. So the question is, why is 3 to 5% of chromium added to this grade of steel more effective than when you have 18% of Prof. Rajiv answers? So these are the questions that I've got here basically. And of course, if you look at this corrosion rates, they are way lower than what is acceptable for implants. And that's really why I'm much more interested in pushing this. But one thing that we found basically that was in the ASCA state, basically the alloys that we first tested were in ASCA state. You find all those dendritic structure, and pitings were really they were promoting pitting. So we even thought, okay, maybe these pits are contributing significantly to the corrosion. I was like, okay, let me get rid of the pits first and see what happens. Okay, and to get rid of the pits, I went back to my piece of equipment, carry out deformation, and we could decide the ASCAS microstructure, we could transform it immediately. And not just one single step, varying temperatures. And we didn't even vary much here because it's just a preliminary study, basically. And I mean, you can see that we had some globular structure there. So we couldn't, at 905 per second, we didn't see anything. So we repeated the corrosion experiment. Yeah, we didn't see dendrites. We repeated the experiment, but the corrosion rate is still about the same as the ASCAS. So this got me confused, and I was like, okay, so I need to start talking to people who probably understand this more. And this is one of the reasons why I'm here. So the first question is, what is how is 3 to 5% of chromium very effective in slowing down corrosion rate? And the second is, even after getting down how they're repeating, the corrosion rates didn't even reduce further. So I don't understand that. But that's the preliminary result that we've gotten now. And for our experiment, we repeat at least 3 times. So this is just to show you that the pits in ASCAS are taken as 172, and magnification is 100. And you can see that in terms of pitting, that's different, basically. So the issue is, I think that these materials could be promising for a biomedical application, but we need to answer that question because we need to be able to say, why is it that having just 3 to 5% of chromium more effective in this manganese-based steel than the popular alloy that we have, 12% chromium and 8% nickel. So, and that's the question that I've brought here, and I hope that maybe I might be able to get an answer. Remember, as Steve Hawkins said, we should work together and hopefully we can have answers. Because if we can crack this, I think that we might be able to produce alternative material that developing countries and middle and low income countries can actually use eventually. So I'm hoping to have some discussion with you. When I'm bored with all the lab work, I do outreach programs basically, and that's taking science to secondary schools. We call it secondary school. What is it called here? High school. High school as well. So this year there will be a competition and collaboration with Cyber, because they're supplying us some very low cost potential start to do some demonstration, which is really good. Again, and I had some very fruitful conversation with Prof. Tuo, and hopefully we can also get talking more. So this will be happening. They will be coming to our university on the 19th of August, and we have already 51 learners that will be showing some, nice stuff that we do in metallurgy. Because one thing that we have seen in the last 5 years is that a lot of people are not interested in material science and engineering. Everybody wants to go into IT and coding. But all those materials you use to build robots and all that, they come from material science and engineering. So we're trying to take this down to high school, maybe captivate their interest. So basically, one of the things that it's not really sustainable, basically, because so one of the things that we did, we're going to be doing this experiment, and also this experiment just generating electricity and lighting LED bulb from lemon fruits, basically. And yeah, so this is really not sustainable because, it's food. But one of the things we're also thinking of is maybe if we could use waste from all this extracting electrolytes and all that. But this only happened a week before I left, so hopefully we have some ideas in the future. So this was in 2022 when I had an outreach in biomaterials, basically. And they came to a lot of the kids were quite happy. So we also partner with AfriMine. So in terms of Prof. Veronica was talking about having some collaboration in terms of, because we have access to mining industries around in South Africa and all that. And there is actually a network that has, mineral professionals and graduate students online, and they have representatives in all sub-Saharan countries in Africa. So we're working on them on the outreach as well, so that we can change the narrative that material science and engineering is not a bad discipline. We are not the one destroying the world. We know that some of our practices are not good, but now we're making it to be much more sustainable. And I know I've kept you here for too long, I'm sorry, but thank you so much. So thank you for having me. Prof. Rack, sorry, I looked for your picture, I didn't find it. I don't know how to put it. These are the people that have made my stay wonderful, and every one of you. Thank you so much.
Where did you find that?
Well, it seems like we fancy person a lot of
Questions?
Thank you very much for the wonderful talk. Toward the low density alloy, what you present is basically still a bulk material, but with different elements added in, right?
Yes.
Like the bone structure itself actually has a lot of micro holes and this kind of networking structures. Is that possible to create some microstructures into the alloy to mimic this kind of structures and make it low density?
Yeah, so if you see, like even in titanium, one of the ways they're trying to reduce the elastic modulus for that and the cost is to do some additive manufacturing processes where you produce porous titanium alloys. Even in magnesium that has recently been approved in the US, but I would say be careful because then it comes to corrosion. Magnesium does not really have any integrity. So this is just like a preliminary stage, basically. In the long run, that's what we would aim for, to be able to produce those kind of structures. And don't forget, oftentimes you don't totally replace the bone. It's an implant, so it could be screws, it could be that implant connecting, joints together. So it has to be connected to your bone inherently, in any case. But yes, definitely there are methods of making all those porous structures and all that, and they're already doing that with titanium and magnesium and all that. And I think that if we get still to that point, and it's low density, then it will even be cheaper than that. So, but that's like maybe 5-10 years from where I am now.
I see. Thank you.
Other questions?
Hey, Michael, really nice talk, really enjoyed it. A lot of useful and a lot of new information there. I have two questions. I guess I missed something. So one was, when you were talking about iron, manganese, aluminum alloys, did you look at whole chromium content, effect of chromium content, like going to very high chromium and low chromium?
Okay, so like I said, it's also like, we did this year. It's very little resources. So the reason why we stayed at 3 to 5 was because we actually did a lot of literature search. So they actually reported that as the optimum. Because now, I think the argument is when you begin to have more than 5, you start finding some crazy carrots. That also brings it down. So we did it, we just kept the work within the composition that we reported in literature. But it would be nice to really confirm. What really got me curious is how can you argue that 3 to 5% chromium added to manganese base steel gives better corrosion resistance than 016L stainless steel that we've been using for years. So I just wanted to double check that, and I found that basically. But the question is if it works, what's the mechanism? Nobody is explaining it, even the almighty rabbis don't explain it in their paper. So that's one of the things that I thought maybe.
That's very interesting, very interesting.
Yeah, so, and the same goes with titanium as well. Like you had iron to it, it slows down the kinetics. So what's happening to the solar spin? I know through SPS we could get some answer, X-ray photo electron spectroscopy. Send my student to Turkey to do that. Yeah, but I mean, we still getting the results. But of course, if we could have other fruitful discussion on this.
Yeah, definitely. We get a lot more understanding at lower length scales and all that. But yeah, that is great. One more question I have about titanium alloys. So I'm just curious. I don't know if you checked that or not. If you had iron, how does that affect the solubility of oxygen? If you check that, or you can comment on that.
Yeah, absolutely. That's usually, I use, if you don't search enough, you even think that you're probably the first. In my mind, I thought I was probably the first to make this cocktail, the alpha beta region. But I realized later, after many years, I think this year, that actually an alloy similar to what I've produced, just a slight bit, has also been produced like here in the US, basically. And one of the things they were worried about is the interstitial content. And you can see, before we thought, okay, the hardness and all that could have been influenced by oxygen content and all that, because with iron, it oxidizes, and you can have those oxygen content that you measure. But one thing about this alloy is that, even as reported by some research work done on similar alloy in the US, is that it allows you to even have higher threshold of oxygen with still acceptable properties compared to TI64 basically. So we don't have a system that could help us vary into iron nitrogen content and all that. But we did measure it, and ours was within spec. That's why the fact that we use a facility that's not meant to actually cast titanium. I hope that answered the question.
Yeah.
Any other questions?
Have you done any grain boundary analysis between your high and low concentrations of varying?
No, that's all. Yeah.
Okay.
Question, maybe I can. Have you looked at the diffusion properties of the elements that you're adding to your alloys? Because if you think about it, when you add chromium and manganese into an alloy such as steel, steel is technically pretty low oxidizing element compared to all of these later transition element metals. Right? When you add chromium and manganese, your surface is going to change based on what you start adding into that system. With the addition of chromium, for example, chromium and manganese are very likely to oxidize compared to your iron, right? Therefore, you kind of start, I think you start having double passivating layer oxide, and probably having more and more of that passivating oxide layer might actually protect the iron itself, or the steel that you're making down the line. But
yeah, we've not looked at that.
Yeah.
I mean, that's a good explanation. But my question is, if you now have lower content of chromium, and it's giving you
but you have manganese now too.
Manganese, okay, that's a good question. But do you know, from what we've found in literature, manganese is actually very poor. It's really just dissolved. So, but I mean, I get your point. I'm just saying, manganese, it's really, compared to iron,
Some of the work that Andrew is doing, I think, can explain.
So I mean, I don't have answers. That's why I'm here. So, and thanks for that. And probably would have it. But we also don't have some of those capabilities, and that's why I'm here to work together with you. I mean, And if we can find answers to it, that would be
Can I actually piggyback on that? Because in looking at this our design, you start with a desired property or attribute. But then the question is, what is your guiding principle?
okay. So
Because I look at it, the alloy you talked about, there's a lot of fast road transition metals.
yeah.
But if you go back to the basis of mixing and stability, stabilizing those sort of solutions or whatever you try to target, there's going to be a question of balance shell interaction, which would now start sucking you down to start looking for tungsten. And looking at the periodic table, titanium is right perfect diagonal to tungsten. Has anybody started exploring those heavier additives?
I know there's, okay, so for example, so I found it quite weird. I don't understand it fully. There's a review paper that was sent to me. Actually, I couldn't even review it. People were even exploring tungsten as a biomedical alloy, and I really don't understand because I've never worked with tungsten before. I just said I can't do it. So I think some people might have been working in the direction. But with us, so the way it works, because we don't probably have a lot of capacity and capabilities in terms of all those atomistic simulations and all the simulations that I have done here. But we have like a thermocarc, which we use to try and simulate different compositions of alloys, and then it can give us desired phase. So what we work with is what are the phases that have been reported in literature that would give us targeted properties. Then we can then pick compositions and do simulations of thermocarc, and we can have some ideas based on that. So I don't know if I answered your question, but that's the key. So we have targeted properties, we have information from literature, what phases or kind of microstructure that could lead us to that. So, and in terms of phase stability and all that, so we start with thermocarc simulations and we can do that. Yeah, I know quite a few people are beginning to develop capabilities in terms of DFTs and all of this now in South Africa, and they would actually be very useful in helping us work for. Yeah, but you can only.
Yeah, but you know, Michael, we challenge that though, because you have a lot of equipment.
Yeah,
before the DFTs and the thermocarcs, there was delta G, right?
Yes, absolutely.
Right?
Yeah.
So in everything, even those DFTs and the thermocarc, all of them go back there. And I see it as an opportunity actually to have less. To have less is actually an opportunity to get better solutions.
Yeah.
Because you looking at what you have, one of the things that was coming from the 90s, just compute the free energies of the calculator. Just
First
piece of
principle.
information. First principle, with a pen and a pencil, a whiteboard like one behind. And then maybe you can get a better solution that is not biased by the assumptions in use of these advanced techniques.
Yeah, I totally agree with you. It's one of the conversations that we had yesterday. I've already prepared the talk, so I was going to share it anyway. So, but I mean, to get insights on alternative ways of looking at things, and I think it's one of the things that I like.
Thank you.
I had a quick question. So you talked about strain rate and the temperature, and you trying to find the sweet spots, right? So
Trying to find the
sweet spot, like
Okay.
the microstructure regime you were
Yeah.
doing, right? The globular
yeah.
R5 galaxy. So there, what was the influence of strain to the amount of plastic deformation?
Okay, that's as different. So, so there is also an optimum strain, basically. So that's why, I don't know. Some people have actually critiqued this dynamic materials modeling, but I think it does a great job, basically. So if you go to, there is an optimum strain for you to achieve those globular microstructure. As you can see, I didn't have a full globular microstructure in the entire system. I just needed to deform to a higher constraint. That usually give me the results that I want. If I want like 100%.
So these experiments were done in lab.
In the play room,
And you are pulling the sample out.
No, compression. Compression, yeah. So we're doing compression. But always we're at a fixed strain, okay? So, but if you increase the strain, then definitely you have more deformation happening, more lamellar rotation, breaking of lamella, and of course, you have to get microstructure. Yeah. So strain doesn't affect.
Can we do some experiments there?
Yeah, and that was what I was mentioning yesterday.
Any other questions? Okay, if not, let's thank the speaker.